In this video, we're going to discuss vapor pressure. So, vapor pressure is an interesting gas law component that involves liquids and even solids turning into a gas. So let's imagine over here that I've got a beaker and it has some water. So there's lots of little water molecules floating around in it. Well, if you think about any large collection of moving objects, if you've ever played pool, think about when you break. In the opening shot, somebody hits and it breaks the balls apart. If you hit lightly, some of the balls move a little ways away and a lot kind of stay right where they were. If you hit harder, more of them move further, but plenty of them barely move at all still. Hitting harder definitely increased the average and caused some of them to move all over the table and bounce around, but there's a distribution. The balls don't all move at exactly the same speed or direction. What this kind of looks like in reality is you end up with something, and it's my favorite graph in all of chemistry, that looks like this. What it says is that some percent has a certain amount of energy. And so what that means is that, some of the balls are moving slow. How many? Well, there's some percentage. There's a different percentage that's moving at a higher energy, so a little bit faster. Well, this keeps going. There's a small percentage that's moving pretty darn fast. And as we get further and further out here, as we get faster and faster and faster, so higher and higher energies means more aggressive movement, there's a smaller and smaller percent, but it never really goes to zero. If you hit hard enough, one of the balls might jump out of the table and go flying off into the next pool table. Like a few of them could be at really high energy. This is true for any large collection of moving objects. This is the bulk distribution. It's just a way to kind of show us that when you have a lot of things, some move really slow, some move faster, a few move really fast, but not nearly as many. The result of this is that most of our water molecules over here, they're bouncing around, they're bumping into each other, they're not doing much. Don't really go anywhere. But every once in a while, one of those molecules at the surface can be bumped into from multiple directions kind of at once, and they all slam into it and just launch that particle up. So one of these particles can just get blasted into the gas phase. It can actually break completely free and just be floating around in the gas now. And it will just drift away on the wind. This is actually how evaporation works. If you have a puddle, why does it evaporate? It's not boiling outside, and yet a puddle of water will slowly vanish. Evaporation is actually this. It is every once in a while one of the particles breaking free and floating off into the air. It just keeps happening. Well, effectively, somewhere along this energy, there's a point where you have enough to break free. So there's a break free point. If any of your particles have that much energy and happen to be at the surface, they can go into the gas phase. The vast majority of your particles don't have that much energy. They're not moving that fast. And even if they are, they might not be near the surface. So most don't escape at any given moment, but a few do. You might have a situation where maybe 10 per second manage to escape. Now that is temperature dependent. This graph over here actually changes as your temperature changes. Think back to the pool. If you hit lightly, most things barely moved. If you hit harder, many of them still moved a lot farther, even if there was a spread on how fast. A hotter object is spread more towards the higher energy than a cold object, or a liquid in this case. Well, go back to your break-free point. What this means is that the hot material has more particles past that break-free point. It had a higher percentage. The hotter you are, the more of your particles can break free. So more of these water molecules end up drifting off into the gas phase per second. Whatever the rate of leaving, so how fast we leave, or 10 per second, would be dependent on the temperature. Go to a higher temperature, so if this was cold, you might have something like 20 per second leaving if you were hot. That rate of leaving, that speed that you depart, that is dependent on your temperature. This is why if you have a wet sock on a cold winter day, it stays wet. Like, it's just uncomfortable, it's constantly wet. If you hang it outside to dry, it really doesn't, it just drips. But if it's a sunny day, a wet sock might actually dry while you're wearing it. And if you put it outside on the porch or outside the door or something, it's probably dry in a couple hours. The hotter day helps that water evaporate quicker. A colder day makes it much harder for the water to evaporate. So, neat property about liquids turning to gases. But what if that container's not open? What if I have a container and it's sealed? I've got a bunch of water, and initially I have a vacuum. There's nothing above the water. It's just an empty container on the top half. Well, over time, so a little bit of time, some of those water molecules are going to break free. And so I'm going to have a little bit up in the gas phase and a whole bunch of water still in the liquid phase. Those things in the gas phase, they're going to float around. They'll bounce off the walls, and eventually they might hit the surface again. So as they bounce around, if they hit the surface, they can get stuck back in the liquid. What this means is I have a rate of leaving, like say 10 per second. Well, there's still 10 per second leaving later, as long as it's the same temp, but now I have a return. Some of them are coming back. Well, if I give you $10 and you give me $2, I'm out $8. Right? But if I give you $10 and you give me nothing, I'm out $10. The speed at which the amounts are changing alters as we build up more particles in the gas phase. And so over time, this will continue to happen. I'll get more particles in the gas phase. They'll be coming back a little bit more often. I'm still leaving at about 10 per second, but now maybe I'm coming back at 7 per second. Eventually, over enough time, I will build up enough particles in the gas phase that I leave and return at the same speed. Well, at this point, I can never get any more into the gas phase. For every 10 I put in, it gives me 10 back immediately, so I haven't increased the amount in the gas phase. So I can never make the return rate get any faster because I can't get more into the gas phase to have them come back faster. This reaches what we call equilibrium. We'll talk much more about equilibrium in many processes in later videos, but for our purposes, it just means that they're happening at the same amount per second. Well, if we think about this top part, well, there's some gas in there, so there's some moles. They're gases, they're bouncing around hitting the walls, so there's a pressure. They're at some temperature, and there's a volume. They're occupying a volume, so I have a gas law component. In fact, if I know the volume of the container and I know the temperature I'm at, I can figure out either the volume or the pressure or the moles. Ends up, if you have twice the size of container, you'll just end up with twice as many moles. What actually ends up balancing is the pressure. Because, well, pressure is pressing on things. You've got to hit things to exert it. You've got to hit the surface of the liquid to have that pressure, which means your return rate is tied to your pressure. And so this is why we call it vapor pressure. The vapor pressure is that pressure of the gas particles released from your liquid. And it has a maximum amount. At any given temp, any specific liquid will have a set vapor pressure. So it doesn't matter how large or small your container, if you have water and it is a certain temperature, no matter where you are, that sealed container will always have the exact same pressure of water vapor in it. Now, it takes a little time to build it up, If you've ever had a water bottle, you took a drink, sealed it, and left it in your car, and you came back later and there were droplets all over the sides, what had actually happened is it took a while to build up pressure into the bottle, and then once it reached it, it could start sticking to the walls, and any that got stuck to the wall, new water from the bulk would escape into the gas, and then that bit on the wall couldn't go back. And so you built up droplets all over your bottle. Or if you ever had a bottle in a hot car and you open it and it kind of sprays out a little bit, where did the extra pressure? Like you sealed it without pressure. Why did it suddenly spray? Because there was an increase as the vapor got into the air. Because even if you had a container that didn't have a vacuum, say it had some normal gas, well, as your water escapes, it's still going to add its own vapor pressure. It's going to kick water into the gas phase until there's enough water in the gas phase to match the leaving rate. And so whatever your original pressure was would go up by the vapor pressure. And so vapor pressure is an interesting property, especially of liquids, but even solids can do this. Solid ice has a vapor pressure. If you've ever had something in your freezer and you left it for a long time, you might have pulled out the packaging and noticed that there were ice crystals all over on the inside, and whatever it was freezer burned. That's actually what freezer burning is it gets dehydrated. The liquid slowly drifts into the gas phase, moves elsewhere in the packaging, resolidifies, and then isn't in the food anymore. And so the food gets dried out. One way you can avoid freezer burn is to package your food really tightly. If there's nowhere for that moisture to go, then it just ends up soaking into the food itself. So vapor pressure, liquids and solids, to different degrees, can break into the gas phase. There will be a limit on how much they can be in the gas phase, though. Once you reach that vapor pressure, that's the maximum. Well, this isn't just a neat aside, because vapor pressure has a very important relation to things like boiling point. When we think about the boiling point of water, generally we think, oh, it's 100 degrees Celsius. And that is true at 1 atmosphere of pressure outside. Unfortunately, if you're somewhere with a different pressure, that's not where water boils. If you've ever read on a packaging where it says higher elevations cook for like 5-10 minutes longer, what's actually happening is that the food isn't as hot when it's cooking. So if you throw some pasta into boiling water, it will get up to 100 degrees, start to boil, and then you throw your pasta in. So your pasta is cooking at 100 degrees, at least down here at sea level. But way up on the mountains, if somebody's trying to grill something or cook something, and you throw in your pasta, that is a terrible stove, but hey, throw in your pasta. Well, you're at a higher elevation. The pressure might only be 0.9 atmospheres. Vapor pressure is tied to boiling point because water is always trying to escape. Lots of the water is trying to drift out and get into the gas phase, but if you have an open top, well, there's tons of gas out here, and it's bouncing into the water. It's shoving that water back down. It's preventing most of it from escaping. The vapor pressure is actually the amount that can slip past based on how fast it's able to escape and move itself through the water molecules. If the outside gas wasn't there, many more of the water molecules would actually break free. So as you reduce the amount of outside gas, you reduce the preventing of the water escaping, and more water can start to escape more easily. Your boiling point is actually when your vapor pressure is equal to the outside pressure. So if you have less outside pressure, you don't need to have as high a vapor pressure before you boil. One way to view that, if you think of a graph, if we have pressure and we have temp. Well, the lines I'm going to draw are vapor pressure. And so water goes like this. This is the vapor pressure of water. And so out here at 100 degrees Celsius, if I want to draw it over, this would be 1 atmosphere. And so it just so happens that for water, this is why we said it that way, but at the vapor pressure equaling 1 atmosphere, that happens when water is 100 degrees Celsius. If you have an environment where 0.9 atmospheres, I don't need to be as hot for the vapor pressure to have reached that pressure. And so I might be down at, say, 95 degrees Celsius by the time I reach that pressure. Since the boiling point is when the vapor pressure equals the outside pressure, I will boil at 95 degrees. And a curious property of boiling is that when you boil, you don't increase your temperature while you're boiling. Until you have fully turned into a gas, you will stay at that temperature. So when we say water boils at a temperature, until it has all boiled away, it doesn't get any hotter. Consequence is at high elevations, your water boils at 95, which means your food isn't as hot when it's cooking. This is why it takes longer to cook. If you throw pasta into room temperature water, it's not getting soft for days. There's a reason we turn up the temperature. Hotter makes reactions go faster. So being at 95 instead of 100 means we're not quite as hot. We're not quite as fast. This is actually an incredibly handy tool. This is how freeze drying works. If you can lower the pressure way down, 0.1 atmospheres or lower, well, I don't need to be very hot. I can be down around room temp. I can be colder than that. You can actually have things that are near freezing and pull an incredibly good vacuum on them, and the moisture will leave. And so if you want to freeze dry food, this is how you do it. You'll reduce the pressure on the outside. We exploit this for all sorts of situations. If you have a chemical and it's dissolved in, say, ethanol, you could boil the ethanol away, or even if it's dissolved in water, you could boil the water away. That means you have to get it hot. Your chemical might not survive the heat. A trick is to, instead of heating it up, pull a vacuum on it. Because there's less pressure outside, your liquid will just boil away, but it will only be at room temperature. And so your chemical never gets hotter, it doesn't get destroyed, but you can still remove the liquid. So vapor pressure is an interesting component of gas laws, and it helps us explain some of the differences in boiling points that we see with liquids. Normal boiling points are defined as at sea level, but as you change the outside pressure, you will change the temperature at which they boil.